Standard machine learning trains models by letting parameters drift freely across an open mathematical landscape. Using stochastic gradient descent, the system chases lower error rates by updating its weights in whatever direction the math dictates. This creates the crisis of unconstrained adaptation. Because the system lacks formal geometric boundaries, it optimizes for a single metric without any structural anchor. Without physical limits on how far or how fast those parameters can shift, the model can wander into unstable regions of the loss landscape. It may learn the task, but it destroys its own operational safety in the process. The industry currently relies on post-hoc software guardrails, elective if-then filters, meant to catch unsafe excursions. But an external filter cannot reliably contain a system that is inherently unbounded. PhaseLoom mandates governed learning. This architecture locks the model parameters inside an impenetrable geometric container. Adaptation is treated as a strictly constrained dynamical system. Every update must resolve within the strict limits of this mathematical boundary. Safety becomes an unyielding physical law built directly into the geometry of the machine's state space. Establishing this governance requires redefining what constitutes a machine state. A simple vector of weights provides no mechanism for internal control. PhaseLoom creates an augmented state tuple. Representation, X, is the operative state locked in an admissible set. Curvature memory, C, is accumulated deformation resisting reckless updates. The learning budget, B, limits deviations. Finally, intrinsic time, tau, measures the density of experience. These four pillars mathematically link every adaptation to historical effort and future safety limits, anchoring the machine as a structurally governed entity. These variables define a global admissible set, a rigid mathematical envelope containing all permissible states the machine can occupy. This equation describes the continuous governed flow. The first half, the raw vector field, represents the unconstrained drive to optimize. The second half is the convex normal cone. When the state touches the boundary, this cone generates the exact outward reaction force necessary to prevent a breach. By subtracting this reaction force from the raw vector field, we shift the architecture from standard differential equations to differential inclusions. The mathematical shape of the normal cone repels the AI from unsafe behavior the moment it contacts the boundary, rendering external monitoring redundant. The learning budget coordinate imposes a non-negotiable limit on this movement, specifically managing systemic risk. In this tracking graph, a budget above zero permits a learning regime, exploring risks that increase task mismatch. When risk fuel hits exactly zero, Theorem 3 invokes hard budget absorption. The task mismatch derivative is forced to zero. The risk line cannot slope upward, only decrease or remain flat. The system enters a mandatory repair-only regime. It can optimize for stability, but its capacity for risk is gone. This geometric halt proves the machine is physically incapable of increasing task mismatch once its risk fuel is spent, defeating any potential software override. Auditing these systems requires a new temporal standard. Linear wall clock time treats idle processing and high-stakes error correction as equally important. This synchronized timeline shows intrinsic machine time. It dilates, compressing and expanding based on the immediate stress of the system. The pace of this internal clock is dictated by a density law, which monitors the machine's state variables. The clock accelerates for task mismatch, or algebraic tension, when rules contradict. Dilation occurs during rapid structural curvature and budget scarcity as fuel dries. Consequently, the machine experiences time faster, logging data at a vastly higher resolution during periods of acute stress. Intrinsic time ensures high-resolution auditing occurs precisely when the geometric risk of failure is highest. To manage this high-resolution data, we have to rethink memory. Standard architectures attempt to log every single parameter micro-update. Storing raw microhistories creates an unmanageable swamp of data. Perfect recall is a systemic hazard over infinite horizons. PhaseLoom employs the projection memory law. The chaotic internal trace passes through a rigid projection plane, distilling into a stable macro memory block. Like a receipt, it preserves only safety invariance. Under Oplax memory composition, merging these blocks creates an envelope mathematically smaller than its raw parts. This irreversible loss of information prevents data exhaustion. It compresses history while mathematically guaranteeing that safety boundaries were never breached. Projection memory replaces data swamps with mathematically stable, infinite horizon audit trails. When the four-part state tuple evolves within the bounded manifold, it generates a continuous, self-governing flow. This architecture bridges the continuous physics of mathematical manifolds with the discrete reality of cryptographic execution ledgers. Because the trajectory is bound by strict Kurdika-Loisaev convergence properties, the system is mathematically guaranteed to stabilize. Safety is no longer dependent on a heuristic filter catching an unpredictable drift. The model operates as a governed subject, constrained by its own internal geometry. Transitioning our safety-critical systems to this rigorous standard of physical bounding is now an absolute industrial necessity for autonomous infrastructure. Machine adaptation becomes an auditable, bounded, and rigorously proven safe evolution.